Numerical analysis of heat transfer enhancement in the single pipe heat exchanger with helical enclosure, He, under constant wall temperature. Abstract: in this investigation the heat transfer mechanism based on the temperature slope among two dissimilar geometry of helical inserts with both cases of distinct nominal pitch lengths and angles and latitudinal lengths at the condition of constant wall temperature. Enhancement of interchanging of heat between wall to flowing fluid in the SPHE.in most of cases generally heat transfer done between two fluids but here itself wall surface and fluid interface. The outlet temperature of the fluid drops suddenly when the Reynolds number increases rapidly 6500 with HIB compared to HIA unpredictable of first case through length and other case middle portion of inserts prescribed size of pitch length and pitch angle at preeminent temperature. Also, the Nusselt number and heat transfer coefficients are significantly changed due to the constant wall temperature condition in the continuous heat exchanging mechanism. Keyword single pipe heat exchanger, SPHE, Reynolds number, Re, Nusselt number, Nu, heat transfer coefficient, HTC, helical inserts, Hi. Nomenclature. Symbol. 1. Introduction. Significant increase in efficiency of heat exchangers, can be realized with enhancement in heat transfer coefficient of fluid. The augmentation is classified into three main techniques: active, passive, and compound. The active techniques require an external force such as electric field, acoustic or surface vibration. The passive technique involves fluid additives, special surface geometries, or swirl flow devices, that is, twisted tape inserts. On the other hand, the compound techniques are created by a combination of two or more passive and or active. Many researchers use the passive device to achieve enhancement in heat transfer by its hassle-free use. Inserts increase residence time and generate swirl effect of fluid flow in the test section of tube causing vortex mixing of fluid particles. An attempt is made in the present study investigate enhancement of heat transfer in a single pipe with helical inserts of different diameter and length in the laminar to turbulent fluid flow region. Detailed experimentation was carried out with single and double strip helical screw tapes in a copper by Shashank Ranjan Chaurasia 3. They conducted that combining the effect of nanofluids and the effect of swirl created by insert would cumulatively augment the heat transfer coefficient. Mr. Salem et al. 4 investigated heat transfer enhancement using continuous helical tape inserts with varying pitch to diameter ratios and ratio of height to clearance between two pipes. Heat transfer enhancement with inserts was observed to be 70 to 164% when clearance was 0.275 to 1. Nusselt number increases of 1.77 times with helical inserts as compared to plain double pipe heat exchanger was indicated by Kashay R. Sharafi 5. Anas El Makal 6 carried out experimentation at varying Reynolds number and baffle plate spacing in a double pipe heat exchanger. Their results showed increased heat transfer from 5 to 45% when baffle spacing is reduced from 100 to 25 mm. Multi-objective optimization, NSGA, is utilized by M. Sheikh Holslam IET7 for forced convection heat transfer analysis using thermal performance was maximum i.e. 1.59 for Re 6000 and open air ratio of 0.05. Niwat Piriyarung Raj 8 investigated numerically the heat transfer enhancement and friction factor is a tube under constant wall temperature. It was observed that heat transfer and pressure loss increase with open air ratio when inserts 1 inserted in the fit tube. Sami D. Salman 9 carried out numerical analysis of heat transfer in a circulated tube with twisted tape inserts under constant wall heat flux and laminar flow condition. Their results indicated increased heat transfer with decreases tube ratios and increase of Reynolds number. MMK Buya10 in the double helical inserts under turbulent flow condition at double helix angle of 9 degree and highest Reynolds number 51,000, while that condition achieved 215% of increased in thermal performance. 2. Modeling. A circular pipe of 40 mm internal diameter and overall length of 3 meters with 2 mm wall thickness is considered for heat transfer enhancement using passive devices such as helical inserts in the fluid domain. The Reynolds number of the fluid flowing in the tube is varied from 800 to 5000. The CAD model of the pipe with inserts is imported into Geometry module of ANSI CFX 18.1 software. After meshing, the required fluid domain with relevant boundary conditions is incorporated in the setup module of the CFX software. The outer wall of the circular pipe is surrounded by hot fluid flowing over the tube as to keep the outside wall temperature constant at 373 K. The Reynolds number of the fluid is varying the velocity of the fluid entering the inlet boundary. The pressure outlet boundary condition is 0. Average state pressure is maintained at the outlet boundary. Two types of helical inserts are used with 14 mm and 9 mm diameter and lengths of 2900 mm and 1600 mm respectively. The CAD modeling the pipe along with the helical inserts are given Figure 1. Fig 1 Helical enclosure inside pipe. Fig 2 Mesh generation. In this Figure 2 the grid convergence study is carried out by varying the mesh from coarse to fine mesh, and the model with 1 nodes are considered for all the simulations. 3. Methodology. In the single pipe heat exchanger is numerically investigated with helical tape inserts are placed inside the tube. In the case of HIA, twisted tapes are insert throughout pipe length, and another case of HIB, twisted tapes are some extent of muddle of the pipe only placed. So, in this both cases flow should same operationally conditions like 1. Flow is incompressible and velocity of the flow is constant for each operating condition in both laminar and turbulent regimes. 2. Assumed to flow should be 3-dimensional, steady and uniform throughout the length. 3. Fluid properties are constant and abandoned gravity and viscous forces. Fig. 4 Re versus TE with HIB. In this study of figures 3 and 4, it is observed that the outlet temperature of the fluid leaving the pipe continuously drops at a rapid rate, with Reynolds increasing from 500 to 6500, the flow regime being partly laminar up to 2300 and thereafter entering the transition zone. In case of HIA, initially the temperature increases by 38 K at 500 RE with reference to without any insert, and thereafter the temperature difference decreases rapidly in the transition zone and eventually becoming almost negligible at Re exceeding 5000. On the other hand, with HIB, the temperature difference is 26 K at 500 RE and finally it becomes 0 at RE 3500. It is also seen that at Re exceeding 3500 the temperature with HIB takes a further difference even below the temperature without HIB, indicating that the convective heat transferred to the fluid is rapidly lost in heating the metallic insert inside the tube, which is not seen with HIA, which could be due to stretching of the insert throughout the length causing gradual heating of the metallic insert from inlet end itself.